In 2026, hacker syndicates compromised over 7,000 enterprise AI servers through a massive, coordinated, automated campaign. The speed of this infiltration was unparalleled. Forensic data indicates that the median time from a server's initial configuration to total root compromise was less than 4 hours. Once the initial breach was secured, threat actors maintained persistent access. On average, these intruders operated inside the compromised AI infrastructure 112 days before being identified. This dwell time is significantly longer than the performance of modern detection systems in legacy server environments, which typically identify intruders within 40 days. The financial impact was driven by the exfiltration of premium OpenAI API keys. This theft enabled hackers to generate millions of dollars in fraudulent billing on the unsuspecting victimized corporate accounts. This crisis illustrates a systemic vulnerability. In the race to deploy generative AI, developers have largely bypassed the core principles of network security. Foundational large language models like GPT-4o and Claude remained secure throughout the campaign. The point of entry was elsewhere. The targets were the AI orchestration layers, specifically frameworks like LangFlow and LangChain, that sit between the model and the enterprise data. These frameworks provide the connective tissue required for AI agents to function, linking vector databases and local memory to models like MetaLlama 3. Many IT departments deploy these orchestration tools without auditing their internal architecture, treating them as secure, ready-made solutions. To understand the scope of the threat, we will conduct a forensic autopsy of the breach, beginning with the user interface and descending into the persistent database. This analysis is critical for DevSecOps teams, who must protect proprietary data lakes from being auctioned on the dark web. LangFlow provides a graphical, drag-and-drop interface for building complex LangChain applications, significantly reducing the coding requirements for developers. A critical flaw in its architecture was the auto-login feature. Designed for local testing convenience, this feature bypassed authentication and was frequently left active when servers were pushed to the public internet. This exposure allowed for the exploitation of CVE 2026-5027, a vulnerability found in the fast API-driven file upload endpoints. The Python source code failed to implement validation on uploaded file names. Specifically, the software passed the file.filename variable directly into an OS path join function without sanitization. Attackers manipulated the post request, injecting a malicious directory traversal string. This string forces the operating system to evaluate the path backward, moving out of the safe uploads folder and into the root directory of the Linux system. By landing in the cron directory, the malicious file is saved as a scheduled job. This grants the attacker root privileges and total remote code execution. Prioritizing interface convenience over input validation effectively disabled the application's entire security perimeter. These AI servers are typically positioned deep within a corporate virtual private cloud, where they are treated as trusted internal assets. Once inside, the attacker's first phase is asset exfiltration. Automated scripts search for .env files to extract unencrypted master API keys and database root passwords. These credentials allow buyers on the dark web to run massive spam or phishing campaigns, leaving the victimized corporation with the bill. Phase 2 involves cryptojacking. The attackers install optimized mining software to utilize the server's specialized hardware. The malware hijacks the parallel processing power of the enterprise's high-value NVIDIA GPUs. This compute capacity is funneled into mining untraceable Monero. In Phase 3, the compromised AI server serves as a bridge for lateral movement. The attacker pivots to target internal accounting and HR databases that are normally shielded by the external firewall. A single unpatched AI orchestration container can quickly become a fortified staging ground for an enterprise-wide breach. Securing the system requires more than just patching the LangFlow GUI or blocking an exposed port. The underlying frameworks have their own risks. LangGraph's memory systems maintain conversational context by serializing chat history and metadata into relational databases. This creates a direct, programmatic bridge between the natural language processing engine and the database layer. While legacy firewalls are tuned to block recognizable SQL syntax, the primary input for an AI agent is a simple conversational chat box, often transmitted as a valid JSON string. Traditional security monitors suffer from traffic blindness. They categorize this traffic as inline business logic because it arrives over a secure TLS connection in a flawless JSON format. A meticulously engineered prompt can bypass the model's guardrails, instructing the system to write specific commands into its own persistent memory log. When the framework retrieves that log for context, the natural language string is interpreted and executed by the database. A command like drop table can be triggered through a standard chat window. Without rigorous sanitization between the NLP engine and the database, unauthenticated users can exfiltrate or delete entire proprietary data lakes. Because this occurs within the authorized flow of the AI application, the Security Operations Center rarely receives any automated alerts. Natural language has become a vector for code execution, making traditional syntax-based firewall rules insufficient. Relying on reactive software patches is no longer an effective strategy for AI deployments. Organizations must transition from perimeter-based security to an uncompromising zero-trust architecture. Under this model, every internal request, including API calls between local Docker containers, must be cryptographically authenticated and strictly limited to least privilege. Secrets management must also fundamentally change. Local .env files should be replaced with ephemeral, auto-rotating keys managed through enterprise vaults. Access control protocols should immediately involve deactivating all auto-login features and placing developer dashboards securely behind enterprise VPNs and multi-factor authentication. Dedicated LLM-specific filtering firewalls can be successfully deployed as reverse proxies to sanitize linguistic patterns before they reach the orchestration layer. In an AI-dependent enterprise infrastructure, absolute trust must be verified for every single packet, regardless of its origin within the network. For legacy systems that cannot be immediately updated, aggressive filtering at the Nginx or WAF layer can provide a temporary safeguard. Infrastructure should be hardened by running AI framework containers in a strictly read-only state, preventing the unauthorized writing of executable files. Nginx rules can be configured to block directory traversal attempts at the API upload endpoint. The configuration scans the URI for malicious characters and terminates suspicious connections. When an attempt is detected, the server returns a 403 error and logs the attacker's IP to a threat intelligence feed. DevSecOps teams should treat every byte of user input, whether it is a simple PDF document or a natural text prompt, as a potential malicious payload designed to compromise the system. The growth of AI capability must be matched by the maturity of AI security. If the critical orchestration layer remains entirely unprotected, these highly intelligent tools will ultimately serve as a primary vulnerability for the enterprise.